we'll start one for the end of chapter stuff. Okay, the first question is problem number 30. It says, look at the solvents that are in this table and choose the what the appropriate solvent would be to dissolve the particular substance. So the rule that we use is like dissolves like. So what we try to do is match intermolecular forces. And typically, we can go something as general as polar versus nonpolar. Right? If we want to look at higher solubility, we can look at very specific properties. So the ratio of dispersion versus dipole interactions, or can it form a hydrogen bond, or things like that to even better match it. On these examples, it tells us, is it a polar compound or not? So we have one that is a polar, one that is a nonpolar, and two compounds that are ionic. So ionic compounds, because of the dissociation process, it involves water. So water molecules have to go around those things. So water is going to be the appropriate solvent for ionic compounds. That one's the easy one. All right, so now the next one is, it tells us it's a polar compound, isopropyl alcohol. It's a polar compound, and then it has an OH group. So we would look for solvents that are polar solvents. So here's our list of polar solvents. So things that have OH groups that could hydrogen bond or have a similar group. So water would work well for that. Methanol would work well for that. Ethanol would work well for that, because they have similar types of structural properties. They have the OH group on it. Will acetone and isopropyl alcohol dissolve with each other? Yes, to some degree, because this is a polar bond inside of the acetone molecule. However, it won't dissolve. It's not miscible with any combination. Isopropyl alcohol probably dissolve about 10% in acetone. That's about it. But 10% may be effective enough. Now, when you look at the other side of it, we choose the one that's nonpolar. Vegetable oils are very nonpolar compounds, so they're typically lone hydrocarbons. So this is CH bond backbones, and they have some type of a polar group, whether it's something like a carboxylic acid. It depends on what type of oil it is, but it has a polar group on one end. But the bulk of the molecule is this nonpolar that has dispersion only. So it's dispersion only forces. So we're wanting to match things up that would dissolve that well. The fact that it's got both a polar and a nonpolar regions means that we need to choose a solvent that has similar types of properties. So hexane is dispersion only. Carbon tetrachloride is a symmetric compound. They're dispersion only. So those are not going to be the most ideal. The better solvents are going to be the ones that have a combination of both nonpolar characteristics as well as a polar bond in them. And toluene, we haven't talked about the structure of toluene yet, but it fits in that category. So either one of these two would work to dissolve the vegetable oil better than hexane or carbon tetrachloride. Now, if I wanted to dissolve vegetable oil at 1%, hexane would work. But if I want to try to make a 30% solution, you could never get that much in hexane. So a little bit can overcome this polar interaction. If I want to try to dissolve a lot of it, it won't. All right, the next one says, which compound would be more soluble in water? And you'll probably have a test question somewhat similar to this. So you just have to quickly look at the structures and be able to go back and do the VSEPR. All right, so one of the compounds is carbon tetrachloride, so CCl4. So it's a carbon with 4 chlorines attached to it. So the idea that it's AB4, a tetrahedral geometry, means that 3 of these are in one plane, and then one's coming out of the board at us, one's going into the board, going back. That's the open dash versus the dash one going the other direction. Okay, the other compound is CH2Cl2. So it's going to have the same arrangement in terms of one's going forwards, and sometimes we draw that one going back with the wedge going that way. So let's make these Cl's and these two H's. Now it is also an AB4. The difference becomes in the differences in electronegativity. Okay, so if we look at electronegativity, carbon's 2.5, chlorine's 3, and all of them are chlorines, but hydrogen's 2.1. So what happens with the one that's on the left, there is a pull that goes from the carbon out towards the chlorines, but the fact that it's a symmetric molecule, those all cancel each other out. So the result is this is a nonpolar molecule. And it's nonpolar means it's not going to be very soluble in water. Now, if we look at the one that's on the right-hand side, what happens with it is there is a pull in this direction from the hydrogen to the carbon, and then there's a pull in this direction from the chlorine from the carbon. So the net result is that everything's pulling kind of in between the two chlorines. So this has a permanent dipole. And the fact that it has a dipole means that it's polar, and polar we associate with likes water. So the one that's going to be more soluble in the system is the one that's non-symmetric. Okay, so I'll ask you, if you look at the old test questions, choose the one that's more soluble in either a polar or non-polar salt. And you've got to choose from a list of a few compounds. But you got to work out the best first to kind of figure that out. Okay, so just quickly look at these. Which one is more soluble in water or hexane? So, and I'm going to just answer these with a W or an H. And I'm looking for what does water have versus what does hexane have? Water is the OH bonds. It can hydrogen bond. Hexane is 6 carbon in a row. And they're just surrounded by the hydrogens. So CH3, CH2, 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 CH3. So it's only dispersion forces. So when I look at the types of interactions that occur, which one is going to be most fitting? So if I look at this one, there's no polar bonds associated with it. There's nothing that can H bond. This is going to be something that's more soluble in hexane. All right, if I look at sucrose, sucrose has got all these OH groups. OH groups are like water. It's going to be more water soluble. Isobutene, it's only carbon hydrogens. It's going to dissolve in compounds like that. Now the one down at the bottom is a little bit of a mix of, because it has both some CHs in it as well as the OH groups. But remember, the OH groups are the super dipole. And the fact that this can hydrogen bond twice, ethylene glycol, is much more soluble in water. All right, so this one, 37, is talking about calculating the heat of hydration for a compound. And we went over this slide in the notes very, very briefly, talking about the intermolecular forces we had to overcome. This actually wants to, I didn't do any of these calculations in the notes. It wants us to calculate the heat of hydration for silver nitrate. So silver nitrate is a silver molecule with a nitrate. It's an ionic compound. So whenever, and this is an example from KCF, but it's also a 1-to-1 charge, 1 cation plus cation, 1 plus anion. If we look at the energy involved with that, we have to first pull the ions apart, so separate the ions. That's called the lattice energy. So that's the energy to pull apart. The lattice energy represents this guy. Then that gives the individual ions in the gas phase, and then we bring them back together. And when we bring them back together, this energy that's produced is called the heat of hydration. And it's always a negative in the sign. So it's exothermic, giving energy off. It releases energy in the environment. The heat of the solution is the difference between the energy required to pull them apart versus the energy that's released. So the heat of the solution is typically, it could be exothermic or endothermic. So depending on, we talked about the heat packs versus the cold packs. Sometimes it's significant, sometimes it's not very much. In this case, it's 2 kilojoules per mole. You'd barely be able to feel the temperature difference. Okay, so on this particular problem, it tells us the heat of solution. So we know what this term is. All right, we know what the heat of the solute is to separate the solute. That's the lattice energy in this, so we know this term. We're looking for this term in the system that's got to be negative. So if we want to calculate what is the heat of hydration, that's the term we call it, delta heat of hydration. It's just the difference in those two. Okay, so it's equal to the lattice energy, and this is misleading. It's not 820, it's just a dash there. That's always requires energy to make that occur. So it takes energy to pull these ions apart. That's really, it represents positive energy. I don't know why that dash is. Let's copy that out of the book. All right, so it's the heat of solution, which is 22.6 kilojoules per mole, plus the lattice energy, which is 820 kilojoules per mole, and it's going to be slightly less than, when you subtract those two, whatever it is, slightly less than 800 when you take the difference. And it's a negative on the sign. So it's a negative 794 kilojoules per mole. I think I gave you a mastering chemistry problem like this, and that's the reason I'm working this one. So I'm pretty sure I gave you a problem like this guy. Okay, so you've got a solution that has 32 grams of potassium nitrate for 100 grams of water at 25 degrees, and I want to know is the solution unsaturated, saturated, or supersaturated. So to work this problem, we need to find the potassium nitrate line. So that's this green line right here. And then we need to go to those points. So there's 32 grams of the solute, all right, per 100 grams of water. So that would be right in here somewhere, this going across this way. And then I need to know at 25 degrees. So that would put it about right here. Okay, so on this case, where are we in the system? So if we're below the line, we're unsaturated. All right. If we're on the line, we're saturated. All right. And if we're above the line, we're supersaturated. Yes, that's supersaturated. In this case, we're below the line, we're unsaturated. So we just choose unsaturated. All right. So another one kind of like this. 44 says you got a solution of KCl. So now KCl is going to be this blue line. And it says there's 42 grams per 100 mils of water. It's initially at 60 degrees, and it's cooled from 60 degrees to 0 degrees, and wants to know what happens during the cooling process. All right, so we just figure out where we are. So we're at 42. So 42 would be right across here. So somewhere like it going across here. And then at 60, so it would be about right here is where we are initially. All right, so we start to cool it. So we don't change the amount of the solute that's there. All the thing we're doing is changing the temperature. And as the temperature goes from 50 or from 60 to about 50, nothing happens. So as we cool from 60 degrees to 50 degrees, nothing. But as soon as we cross the threshold, whatever that is, looks like it may be 48, slightly less than 50. So maybe 48 and below, it starts to precipitate. So it starts to form a precipitate. So you're going to start snowing out the solution, much like we have at the owl, the different things. Okay, so just understand what's happening with the heating cooling curve and solubility. 50 is Henry's law. So use Henry's law to determine the molar solubility of helium at 1 atmosphere pressure. So this is 1 atmosphere is kind of boring because Henry's law constant is just the solubility of the gas is equal to the K sub H times the pressure of the gas. And if it's 1 atmosphere, it's just equal K sub H is equal to the solubility. So in our case, the solubility is equal to the K sub H for that gas. It's helium. So 3.7 times 10 to the minus 1, or 0.37. And the units are molarity per atmosphere. And then times 1 atmosphere. Atmospheres just cancel out. So 0.37 atmospheres. If it's anything other than 1 atmosphere, We just multiply by that. So Henry's law is really simple to use. You just have to recognize, if you want to calculate the molar solubility of a gas, this is the equation that I use. This gives it away because usually I don't think I've ever asked that question where I've asked what is the molar solubility of gas, not using that. Yes.
How do you get to -1?
How to get what now?
To the negative 1.
I glanced at that wrong. Sorry, I was looking at the line above it. It's -4. So 3.7 times 10 to the -4. Thank you for asking that question. Yeah, it's this number. Okay, so let's do some concentrations. So I've got a solution that's potassium nitrate. It's got 72 grams. It's diluted into a total of 2 liters. I want to know what is the molarity, the molality, and the percent by mass. So I actually have this problem, same problem. Maybe I don't. I thought I had the same problem a couple of slides. Maybe we can fit it all on one. Okay, so the first one it wants to know is the molarity. So molarity, capital M, is I want to know the moles of the solute, which is ammonium nitrate, per liters of solution. Okay, so start with what you know. You've got 72.5 grams of potassium nitrate. I need to convert that from grams to moles. So to do that, I need the molar mass, and I've calculated the molar mass is 101.1. So there's that many grams of potassium nitrate per 1 mole of potassium nitrate. So now I've got the moles of solute. I need to divide that by the liters of solution. So it tells me that there's 2 liters of solution, so I just put that on the bottom. In terms of my units, grams and grams cancel out. I've got moles over liters. That's where I want to be. So the problem's set. So that's the easy one. Uh, 143. May I get that? Did I get that? Okay, maybe I put numbers in wrong. And I did, yep. I multiplied instead of dividing. About that. Yeah. 0.359. Right, the next thing it asks for is the molality. So with molality, lowercase m, I want, again, the moles of potassium nitrate. So the first part of the problem is going to be the same, divided by the kilograms of the solvent in this case. Okay, so first portion is going to start the same to get to moles of the potassium nitrate. 101.1 grams per mole. So now we got the first half of it done. So now we got to figure out the amount of the solvent that's there. Okay, so I know the what do I know? I know the density of the solution is this. So knowing the density and the volume, so the density, I'm gonna put this down below it, a different color. So density is equal to mass divided by volume. So that says that mass is equal to the density times the volume. So the density is 1.05 grams per milliliter. And I've got 2 liters. 2 liters is equivalent to 2,000 milliliters. Milliliters cancel out. That's going to tell me my grams solution. So that's 3,010. When I multiply that out, 3,010 grams of solution. But I know in that solution, there's this much of it is the solute. All right, so less the 72.5 grams of solute. 3,010 plus the 72.5 gives me 2937.5 grams and put that in kilograms, 2.94 kilograms. So going back to once I've got my moles, now I just need to take that and divide it by the kilograms of solvent. And I get the molality is 2.44 mol.
I'm getting a different number for the kilograms of salt.
Okay, so
Applying the 1.05 to 2,000, getting.
yeah, how about that?
It doesn't change it much.
Yeah, it 0.5 times. Yeah, that's what I try to do when I do math in my head. All right, so now subtract that less 25. I should have done it in my head or used the calculator instead of trying to do it in my head. .103. Call me out when I make a math error. So I want us to have the right numbers. How about 353? Okay. All right, the last one asks mass percent. So what is the mass percent? Let me do a. So the mass percent would be the grams of the solute divided by grams of the solution, and then times 100. Okay, so we kind of know most of these things from what we just did. So the grams of solute are the 72.5 grams of potassium nitrate divided by the grams of solution. We just said the solution was 2,100 grams of solution from the density calculation. And then times 100 to get it as a percent. .45%, and we need to specify that it's mass and what the substance is that's the solute. So we'd say 3.45% mass potassium nitrate. All right, let's see what the next one is. So, all right, the next one we're not going to finish in a minute. So, I thought we would make it further through this list than we did today, but we're going to come back in tomorrow, finish these up, and still leave us minimum half the class period to talk about the end of the exam. So we'll finish up doing these. You can finish up your Mastering Chemistry tomorrow night if you haven't already, but bring me your test questions tomorrow. Start looking at this stuff. All right, see you tomorrow in class.